Skyscrapers are engineered to move, sometimes several feet from side to side, and that movement is not a design flaw, it is the very thing keeping the building standing. A rigid, unyielding tower sounds strong, but in a major earthquake, rigidity can be the very quality that shatters it into rubble. So how much sway can a modern skyscraper actually survive before the structure gives way? The answer lies in nearly a century of catastrophic failures, near misses, and quiet engineering revolutions most people never notice. For most of architectural history, builders assumed strength meant stiffness, packing structures with as much rigid material as possible. That assumption collapsed, sometimes literally, when engineers began studying why certain buildings survived earthquakes while stronger-looking ones did not. Rigid structures resist small forces well, but they transmit earthquake energy directly into their frame, concentrating stress at every joint. But here is where the story turns unexpected. The buildings that performed best were often the ones that seemed weakest on paper. Flexible structures absorb and dissipate seismic energy through movement, spreading the load out over time instead of one violent impact. This is the same principle that lets a tree survive a storm while a dry, brittle branch snaps at the first strong gust. Engineers eventually gave this behavior a name: ductility, a structure's ability to deform without fracturing completely. Ductile steel frames could bend at their joints, absorbing enormous energy, while brittle materials like unreinforced masonry simply crumbled. What nobody expected was how much a building's natural rhythm, not just its material, would determine whether it survived. Every structure has a natural frequency, the rate at which it wants to sway back and forth if disturbed. Earthquakes generate ground motion across a wide range of frequencies, and disaster strikes when a building's natural rhythm matches the quake's own. This phenomenon, known as resonance, can amplify small ground movements into violent, building-destroying oscillations within seconds. Taller buildings naturally sway more slowly than short ones, giving super-tall towers an unexpected advantage against certain earthquake frequencies. But here is where it gets stranger. That same slow sway makes skyscrapers dangerously vulnerable to a completely different force: wind. Wind does not strike in a single violent burst like an earthquake. It pushes steadily, sometimes for hours, testing a building's endurance. Engineers quickly realized a structure engineered only for seismic survival could still fail from years of relentless wind-driven fatigue. So architects developed multiple structural systems, each fighting different forces in different ways, often combined within a single building. Moment-resisting frames allow beams and columns to flex at their connections, letting the entire structure absorb motion like a spring. Shear walls, solid vertical slabs of reinforced concrete, resist sideways forces by acting like a rigid spine running through the tower. Braced frames add diagonal steel supports, triangulating the structure so force travels along predictable paths instead of concentrating at joints. What nobody expected was that the most effective solution might not be inside the building's frame at all, but underneath it. Base isolation places a skyscraper on flexible bearings between its foundation and the ground, decoupling it from the Earth's violent motion. During an earthquake, the ground can jolt violently while the isolated building above barely feels the disturbance at all. These bearings, often layers of rubber and steel, or specially engineered sliding surfaces, absorb the shock before it ever reaches the structure. Mexico City's soft, ancient lakebed soil famously amplifies earthquake shaking, making isolation systems especially critical for its tallest buildings. But here is where it gets stranger. Some of the most advanced isolation technology owes its design to something as simple as a bearing. Lead rubber bearings combine flexible rubber layers with a solid lead core, allowing sideways movement while quietly absorbing seismic energy as heat. Friction pendulum bearings work differently, letting a building's foundation slide along a curved surface, using gravity itself to recenter the structure. Mexico City's Torre Mayor sits on 98 such bearings, engineered to let the tower ride out even severe seismic events largely undisturbed. When completed, Torre Mayor was tested against forces far beyond the strongest earthquake recorded in the region's history. So if isolating a building from the ground works this well, why isn't every skyscraper built this way? Base isolation is remarkably effective, but it is also expensive, space-intensive, and structurally complex to retrofit into an already standing tower. For extremely tall buildings, engineers needed an additional weapon, one that could actively fight motion happening hundreds of meters in the air. That weapon is the tuned mass damper, an enormous counterweight suspended near a skyscraper's peak, designed to move opposite the building's sway. Taipei 101, once the world's tallest building, hides one of engineering's most famous dampers behind glass near its 90th floor. A steel sphere weighing roughly 660 metric tons hangs suspended by cables like a giant pendulum. But here is where it gets stranger. This massive ball is not there to stop the building from swaying, it is there to help it. As wind or seismic force pushes the tower one way, the pendulum swings the opposite way, canceling out much of the motion. During a powerful 2015 typhoon, the damper reportedly swung nearly a meter, visibly absorbing energy that would otherwise have hit the structure directly. Engineers tuned these dampers precisely to a building's natural frequency, turning a passive weight into an active counterforce against motion. What nobody expected was how quickly this idea would spread from a single landmark tower to skyscrapers being designed worldwide. Shanghai Tower took the concept further, combining a massive damper with an entirely new approach to the building's shape itself. Its exterior twists nearly 120 degrees from base to peak, a design choice driven by physics, not aesthetics alone. That twisting form reportedly reduces wind load on the structure by roughly 24% compared to a straight-sided tower of the same height. Less wind force means a lighter structural frame is needed, saving material while simultaneously improving the building's resistance to sway. But here is where it gets stranger. Sometimes the deadliest threat to a skyscraper isn't the earthquake itself, but a flaw nobody noticed until years later. In 1978, a structural engineering student examining calculations for New York's newly built Citicorp Center made an unsettling discovery. The tower's unique support columns had been analyzed for straight-on wind, but never for wind striking diagonally from a corner. Under quartering winds, stress on certain joints could exceed safe limits, and the original bolted connections had reportedly been altered during construction. The tower's structural engineer recalculated the numbers himself and reportedly concluded the building could fail in a storm expected roughly once every 16 years. What nobody expected was how the response to this discovery would become a legendary case study in engineering ethics. Rather than conceal the flaw, the engineer reported it, and crews worked through the night for weeks welding steel plates over every vulnerable joint. The repairs were completed quietly, largely unnoticed by the public, and the building has stood safely for decades since. The case became a turning point in the industry, reinforcing how seriously engineers now treat even a single overlooked calculation. Beyond dampers and isolation, modern skyscrapers increasingly rely on structural systems built specifically to handle their own extreme height. But here is where it gets stranger. The tallest buildings often borrow their core strength from a shape found in ordinary drinking straws. A hollow tube resists bending far better than a solid column of the same material, distributing force efficiently around its outer edges. Many super-tall towers use this tube principle, wrapping their perimeter in closely spaced columns that act together as one giant hollow cylinder. Outrigger and belt truss systems connect this outer tube to a central core, letting the whole building resist sway as one unified structure. Mega columns, some large enough to contain an entire room, anchor these systems at a building's base, carrying enormous concentrated loads downward. What nobody expected was how much modern seismic engineering owes to Japan, a country forced to rebuild after devastating losses. After the 1995 Kobe earthquake killed thousands and destroyed vast sections of the city, Japan overhauled its building codes with startling speed. New regulations mandated stricter ductility requirements, more rigorous testing, and wider adoption of base isolation and damping technology nationwide. When the 2011 Tohoku earthquake struck, many modern high-rises in Tokyo, over 200 kilometers from the epicenter, swayed dramatically but suffered little structural damage. Engineers later called it one of the largest real-world validations of seismic design theory in modern history. But here is where it gets stranger. Engineers do not just design buildings to survive an earthquake once, they test them against thousands. Shake tables, massive platforms capable of simulating real seismic waveforms, let researchers subject full-scale building sections to simulated earthquakes under laboratory conditions. Computer models now simulate thousands of potential ground motions before a single support beam is ever poured or bolted into place. Sensors embedded throughout modern towers continuously measure sway, strain, and acceleration, feeding real-time data back to structural monitoring systems. Some advanced buildings use semi-active or fully active damping systems, adjusting their resistance in real time as an earthquake unfolds. What nobody expected was how much artificial intelligence would begin reshaping the way engineers predict a building's seismic behavior. Machine learning models trained on decades of earthquake data now help engineers identify structural weaknesses long before construction even begins. Some research teams are experimenting with self-adjusting dampers that use algorithms to fine-tune their response within milliseconds of detecting ground motion. Smart sensors can alert building managers to subtle structural changes over time, long before those changes become visible or dangerous. But here is where it gets stranger. As buildings grow taller, engineers face challenges physics alone cannot fully solve. Super tall towers pushing beyond half a kilometer in height must contend with wind and seismic forces that barely existed in earlier design manuals. New composite materials, higher strength concrete, and advanced steel alloys are constantly tested to push the limits of what a tall structure can survive. Some future designs even propose distributed damping systems, spreading counterweights across multiple floors instead of relying on one massive mechanism. Urban planners in seismically active cities now factor building sway distance directly into how closely towers can be constructed next to each other. A skyscraper swaying several feet at its peak needs enough clearance to avoid colliding with its neighbors during a major earthquake. What nobody expected was that surviving an earthquake might come down to something as simple as leaving enough empty space around a tower. Every one of these systems, dampers, isolators, ductile frames, computer models, exists for a single unified purpose: buying precious seconds during chaos. Those seconds are often the difference between a building that sways safely and one that fails catastrophically. Every certified weld, every calibrated damper, every isolation bearing represents decades of hard lessons learned from real structural failures. Skyscraper engineering did not become this sophisticated by accident. It was built scene by scene, disaster by disaster, discovery by discovery. The next time you stand inside a super tall tower during a strong wind or distant tremor and feel it gently sway, that motion is not danger. It is one of engineering's quietest, most remarkable achievements, a building intentionally designed to move so that it never has to fall. Somewhere right now, in a city built on shifting ground, a skyscraper is swaying exactly as it was designed to, patiently surviving forces built to destroy it.